Have you ever wondered why real-world wireless networks, such as Wi-Fi routers or cellular towers, never seem to achieve the theoretical speeds promised by scientific principles like the Shannon capacity? It's a common question that puzzles tech enthusiasts and engineers alike, as they observe daily the frustrating discrepancy between lab ideals and everyday performance. This video delves deeply into the significant gap between theoretical maximums and practical limitations in wireless communication capacity. We'll explore the complex factors, from noise to hardware issues, that consistently prevent networks from reaching their full theoretical potential in real world deployments. The foundational Shannon-Hartley theorem, mathematically expressed as C equals B log base 2 of 1 plus SNR, defines the absolute maximum theoretical data rate for any communication channel. Here, C represents the channel capacity in bits per second, B is the available bandwidth in hertz, and SNR is the signal to noise ratio, a crucial measure of signal strength relative to background noise. However, in real world conditions, various sources of noise and interference drastically reduce the effective signal to noise ratio from its ideal value. This degradation directly impacts the achievable capacity, forcing it far below the theoretical limit predicted by the Shannon-Hartley equation. Interference from other devices, adjacent channels, or multipath propagation is a primary culprit behind this shortfall. Signals bouncing off walls, buildings, or other surfaces create multiple delayed versions that overlap and cause destructive interference at the receiver. Furthermore, hardware imperfections in antennas, amplifiers, and transceivers introduce additional limitations that compound the problem. These components, despite advanced engineering, are never perfectly efficient, resulting in inevitable signal loss, distortion, and reduced overall performance. Mobility introduces yet another significant challenge in wireless networks. As users move through environments, their connection quality fluctuates wildly, necessitating frequent handoffs between access points, which adds substantial complexity and overhead to maintain reliable service. Protocol overhead further erodes efficiency, as error correction codes, acknowledgement packets, and various control signals consume a notable portion of the available bandwidth. These essential mechanisms, while critical for reliability, inevitably reduce the actual throughput available for user data. System designers must constantly navigate tough trade offs, carefully balancing factors like power consumption, coverage area, and maximum data rates. Optimizing one aspect, such as extending coverage, often requires compromising on another, like sacrificing higher speeds or increasing power usage. Ultimately, wireless capacity in the real world is not solely limited by bandwidth availability. Instead, it's shaped by a complex interplay of interference, hardware constraints, mobility challenges, and protocol overhead, all working together to cap performance well below theoretical ideals.